11D. So we have an IQ test, two different forms, Form L, Form M. They both average 100 and they both have an SD of 15 with an R value of 0.8. Does a score on L predict a score on M very well? Yeah, it does a really good job. 0.8 is a very high R value. True or false? The regression line for predicting the scores on Form M from L has an RMS error of about 9 points. How do we calculate the RMS error? We're going to do the square root of 1 minus 0.8 squared times 15. So true. Suppose the scatter diagram looks like 1 below. If someone scores 130 on Form L, the regression method picks 124 for the score on Form M. True or false, and explain. This prediction is likely to be off by 9 points or so. So this is B. So we would expect that if we go up 9 and down 9 and we draw parallel lines, we should capture 68% of the data. Okay? And for any particular point, we would expect it to be off about 9 points. Is that what the back said? Sometimes I miss something, yeah? That's what I think it is. No, that was B. And then C, repeat if the scatter diagram looks like 2. Right, the higher we get, the less predictive it's going to be. What if the score was, say, 80? Then it's going to be pretty close because that left side is very narrow, but the right side is all sorts of messed up. So it's not football shaped, so the RMS error isn't going to work. 2. Find the RMS error of the regression line for predicting son's height from father's height. So we're using fathers to predict sons. How do we calculate the RMS error? Square root of 1 minus the R value times the SD of Y, 2.7. So 2.33. If a father is 72 inches tall, predict his son's height. So we would it's something like this, right? It's not terribly football shaped. 0.5 isn't too predictive, maybe a little narrower than that. That might have been exaggerating it. But we know that the dad is 72 inches tall. So the average dad is 68. So how much did we increase? We added 4 inches. Now what do? We have to turn that into an SD. So we divide by 2.7. So 4 divided by 2.7. What does that number tell me? This father is 1.48 SDs larger than the son. Or sorry, larger than the average dad. So the son would be expected to be 1.4 SDs times R. If the correlation was perfect, if R equals 1, then the movement to the right in terms of SD will be equal to the vertical movement in terms of the SD, but this graph is only 50% accurate. So we go right 1.48 SDs and we go up 1.48 SDs, but we've got to times that by 0.5 to bring it back down to hit the regression line. So we multiply that by 0.5. So we're actually set 0.74 SDs up, which in terms of inches times 2.7 is 2. So a dad that is 4 inches taller than the average father is expected to have a son that is 2 inches taller than the average son. Okay, so 69 plus 2 would be 71. Okay, where are we? See? The prediction is likely to be off by is it going to be the SD or the RMS error? We've chosen a particular son. Is it going to be 2.7 or is it going to be 2.3? 2.3. Because we used an actual X value to predict the Y value. The Y values in general are off by 2.7. But when you pick an X value, that makes your Y values more accurate. So it would be the RMS error 2.3. Okay, 66 inches tall. So the dad is now 66 inches tall, which is a loss of 2 inches. So 2 inches divided by the SD is 0.74 SDs. So we would expect the son to be shorter by 0.74 SDs times the R value. So multiply that by 0.5. And then I multiply that by 2.7. And that number tells us that we would expect the sun to be 1 inch shorter than the average sun. So it would be 68 inches. And how far is that likely to be off? The same 2.3. All right. Number 3. Find the RMS error of the regression line for predicting income from education. So we have education level and how much they make. So the R value is 0.37, square root of 1 minus 0.37 squared, times the SD of Y, which is $20,000. Is this a very good predictor? Not even close. It's a terrible predictor. So, on average, do people who go to more schooling make more money? Yes, because R is positive. But can we predict somebody's income if all we know is how much money or how many years of schooling they took? No, because it's all over the map. R is 0.37. That's terribly inaccurate. But the RMS error is 18,580. Predict the income of a woman with 16 years of education. So the average right here is 13 and 18,000. So a woman with 16 years of education, that is plus 3. What do we do with that number? Divide it by, oh, I don't even have it on there. So we want to predict this person here. If a woman has 16 years of education, that means she has 3 more than the average woman. Now what do we do? Divide that by the SD, divided by 3.4. Oh, geez. 3 divided by 3.4. What does that tell me? She's 0.88 SDs higher than the average woman as far as education goes. Now what? Now we need to go up 0.88 SDs times the correlation coefficient. So we want to go, this is 0.88 SDs. We want to go up 0.88 SDs, but the R value is so terrible, we can't go up 0.88 SDs. We have to do 37% of that. So I multiply that by 0.37. And we're actually going to go up 0.32 SDs. Well, how much money is that? The SD of the money is $20,000. So 0.326 times 20,000. And what do I do with 6520? Add that to the 18,000. Why did I add and not subtract? We went up, not down. So 24,520. That was 3B. So this prediction is likely to be off by how much? If we don't know the X value, how much are the Y values expected to be off? The average distance from the average is the SD, which is 20,000. But if you know a particular X value, then your guesses become more accurate, and they become more accurate according to the RMS error. So the RMS error in this case is, when we did this, what did we get? I don't remember. So the square root of 1 minus 0.37 squared times 20,000. Did I not type this in? Okay. Oh, I missed a 0. So 18,580. Okay. So we would expect this answer to be off by $18,600. Okay. Repeat parts B and C for a woman with 8 years of education. All right. So we're going to go down here to 8. So that is a loss of how many years? That is -5 on the years. We divide that by 3.4. So 5 divided by 3.4 is 1.47, but we can't use all of that. We can only use 73% or 37% of that. So it's actually down half an SD. Multiply that by $20,000. And I get 10,882. And I take my 18,000 and I subtract that answer. And I would get $7,117. How much would we expect that to be off? The 18.6. That's the RMS error. Now that's weird. We would expect it to be off by $18,000. What does that tell us about the original graph? It's not football shaped, right? Because I ended up with an SD that's larger than the prediction. So that means that it's not football shaped, which income is never normal, right? Income is always right-tailed. And when you look at the scatter plot, a right-tailed plot for the Y values would look something like a trumpet. That's right-tailed. So if you were to graph the histogram for the Ys, it would look like this, because these people have a huge variation. Okay, does that take us, 4. So in that graph, the vertical strip represents the families where the blank is between blank and blank. The ages of the husband are between 19 and 31. Right? That vertical strip starts at 19 and ends at 31. Okay. Fill in the blanks. The average age for all of the husbands is about, where would you put X bar? About 50. The SD is about So about 15, I'd take 15. The correlation between the ages of all the husbands and wives is about. So is this a high correlation or a low correlation? It's pretty high, and there's a lot in the middle and then a couple on the edges. So the correlation coefficient should be, I would say about 0.9, but that's not an option. 0.95. And the reason why it's point. Oh, I skipped B. Sorry, C is 0.95. I'm sorry. So the average for the wives would be about 50 with a SD of about 15. They look pretty close to the same to me. Okay, so we did C. D. Among families plotted in the vertical strip, the average age for the wives is about just that strip, about 25. And the SD would be smaller than the original 15. It would be 5. Okay. And D, the SD is computed for the ages of all of the wives and the wives whose husbands are 20 to 30 years old. Which is bigger? Is the SD for everybody bigger or smaller than the SD of a horizontal strip? Or sorry, a vertical strip. 1 is bigger than 2. The SD of a vertical strip is smaller than the SD of the total. In fact, the SD of the vertical strip is the RMS error, which is always smaller than the SD. Okay? And then 6, the SD is computed for the ages of all of the wives and the wives whose husbands were born in March. Which SD is bigger? So people born in March, does that affect their overall age? No, we would expect, if you looked at everybody that was born in January and everybody that was born in February and everybody was born in March, we would expect all of those groups to be pretty similar, right? Maybe one month has a little bit more than any other month, but we would expect them to be all about the same. Okay, 7, in one study of identical male twins, the average height was found to be about 68 with an SD of 3. The correlation is 0.95. If you had to guess the height of one of these twins without any further information, what method would you use? So what we're doing is we measure one twin and then we predict the height of the second twin. Is there a good correlation? Well, it's 0.95. It's very, very highly correlated. But if you didn't get to look at the first twin, how would you guess for the second twin? You would just guess the average. How much is that average likely to be off? By 3 inches, because that's the SD. But if you know the height of the first twin, then the height of the second twin is going to be more accurate, right? How do we measure the accuracy if you know the first twin? The RMS error does that for us. Okay, so the RMS error is going to be square root of 1 minus 0.95 times, squared, times 3. Come on. So square root that and times it by, oh my goodness, no. What am I doing? So 1 minus 0.95 squared, and then times that by 3. So the prediction without seeing the first person is likely to be within 3 inches. But if we know the height of the first twin, then our guess is expected to be within an inch. Right? Why is that number so much smaller than the original 3? The correlation coefficient is so high. The predictions are very, very accurate. All right. One pair of the twins is standing in front of you. You have to guess the height of the other twin. It's the same answer as B. Okay, and then, for instance, oh, so we would actually need to do it, but we're not going to. You would just you would find the new average according to the just like we did in the last section, right? You'd find how many SDs that is taller, and then you'd go that many SDs up times 0.95, and we would expect that prediction to be off by 0.9 inches. So B is the RMS error. C is a prediction we would use by doing SD right, SD up times 0.9, and then that is expected to be off the same as the RMS error. Yeah. So C, you would use the regression line, and then how accurate is that? Well, it's probably one RMS error away. Okay. Can we do one in E? I won't record it, but just as a review. Yeah, we did all of E. Okay. So we have a regression line, and R is 0.25. That's pretty terrible. Okay. X bar is 68. Y bar is 63. Huh. So I'm going to do one of the problems in E because they're kind of hard. So the XSD, the SD is 2.7, and the YSD is 2.5, and R is 0.25. Okay? So, without looking at the book, what percentage of the women would we expect to be taller than 63 inches? We would expect half of them to be above that. So if I were to draw this line over, and I just look at the women here, that should be half of all the women, if it's normal, if it's a normal curve. Everybody understand that? But if I look at taller husbands, I'm looking at this husband here, how many of those women would we expect to be above average? More than 50%. Does everybody see that? So if I look at all of the women, half of them are over 63 inches. But if I eliminate everybody except for this particular group of tall husbands tend to have tall wives. So if the men are 62 or 72 inches tall, we would expect their wives to be above average. So we want to guess, or not guess, we want to calculate what percentage of the women in that particular column are above whatever we picked, 63 inches. And we would expect it to be higher than normal because this area is smaller than this area. Okay? So, here is the problem. So, this is set E1A. What percentage of the women were over 5 feet 8 inches? Okay? So, 5 feet 8 inches. Darian, watch this. So 5 feet 8 inches. How tall is that? So that is equal to 68 inches. So I draw, this is my my normal curve for the y values. Bryn, come on guys. I know. So we want to find how many women are in this area, right? So how far am I from Y bar to that line? 5 inches. So that is plus 5 inches. I need to take that number and turn it into an SD. So I divide by 2.5 and I get a z-score because that is the SD of the Y values. So the z-score is 2. So how do I find that right-tailed area if z is 2? Shade norm. But in this case, we can just do it in our heads. 2 SDs gives me 95. So how much are in the tails? 2.5 in either tail. So 2.5% of all women are over 68 inches. Okay, but the next question says, if the husbands are 6 feet tall, what's the new percentage? So we're going to go over here to 72. How far to the right did I go? 4 inches, which is 4 divided by 2.7 is 1.48. That's SDs. So I would go up 1.48 SDs times the R value. So times 0.25. So I'm actually only going up 0.37 SDs. And the SD is 2.5. So multiply this by 2.5. And I'm going to go up 1.9 inches. So that woman here is 63.9 inches. Well, no, that's the average. If a man is 72 inches, we would predict the woman being 63.9. You really need to stop doing that. We'll put it on your grade if I hear it again. How about that? So, now what do we do? The new SD is the RMS error. So the RMS error in this case is 1 minus 0.25 squared times the original SD of 2.5. Okay, so we would expect this number to be off by 2.4 in either direction, 2.4 inches. So now we draw a new curve, and the average is now 63.9. And I want to know how many of those women are 68 inches or taller. So that would be 4.1 inches to the right. 4.1 in terms of the SD, which is 2.4. 4.1 minus 2.4, or not minus, I need to divide. So this is 1.7 SDs to the right. How do I calculate the right-tailed area? I would do shade norm from 1.7 to 5. Would I expect that to be higher or lower than this original 2.5? So we're looking at how many women are over 5'8". So 2.5% of the women are above 5'8". But if they have tall husbands, we would expect more. So if I clear out my draw, and then I do shade norm, and I'm going to go from 1.7, is that what it was, to 5, we would expect an answer that is bigger than 2.5. And I get 4.4. So 2.5% of the women are above 5'8". But if the husbands are 6 feet tall, then 4.5% of the women are above 5'8". Yep.